So in the last video I have given you a method how to I have given you a transformation that reduces second order linear equation, homogeneous equation into a second order linear equation, but without having first derivative. So that is an equation, second order equation in standard form or in normal form. Okay. So we will do with an example. So in this video we will give you an example through which we demonstrate this method. So we reduce the equation, reduce the given equation into a simpler equation, so which you can hope to solve. So you actually can solve the reduced equation, and then you find the general solution of the given equation. And also I give you how to find a particular solution of a non-homogeneous equation in the general method, that is called the method of variation of parameters. Having known homogeneous solutions, okay, homogeneous equation solutions of the homogeneous equations, okay. Having known the solutions of two linearly independent solutions of the homogeneous equation y1 and y2, you can find the general solution of the homogeneous equation, okay. So that is c1 y1x plus c2 y2x. This is your general solution of the homogeneous equation. To find a particular solution, we have a general method called method of variation of parameters. What we do is we take the general solution of the homogeneous equation, which is c1 y1x plus c2 y2x. These c1 c2 are constants, arbitrary constants. Now we vary these constants as a function c1x and c2x, and then we look for a particular solution in this fashion, okay, as yp of x, which is c1x into y1x, c2x plus c2x into y2x. y1 y2 you already know, okay, and we want to fix this c1 and c2. We give some, we'll try to find what is the c1 and c2. This is the method of variation of parameters, because these parameters c1 and c2 now we are varying, so that's why the method is called method of variation of parameters, okay. We start with giving an example to demonstrate the method I explained in my last video. So let's do that. So I have seen how to convert a second order linear ODE, homogeneous ODE, into a normal form. Standard form or normal form means a first order derivative will not be there in your second order equation with the sum transformation, okay. So we have seen how it is, how we used, what transformation we used, okay. So you have to use the transformation is yx equal to ux into vx, and that vx should be in this form. So we see some example how we can reduce, so we can solve certain equations with variable coefficients. So let me solve some example. Some equations you can always solve by using this technique. So let me solve. So 4x square. So if you want to solve 4x square y double dash plus 4xy dash plus 16x square minus 1 into y equal to 0. So this is your equation, okay. So what I do is I choose my dependent variable yx in terms of new dependent variable yx ux with some vx. What is this vx? In such a way that when I reduce this equation into an equation in y u, an equation in y I reduce to equation in u, so that second order derivative du by dx won't be there, okay. So let me choose exactly where. So if I use my earlier formula vx, what is vx? Vx is actually e power minus half integral x naught to x. X naught, what is x naught? So you can clearly see that x is positive, okay. So if you don't want this, what you do is either this, or you simply integrate both sides, you will get vx as some constant times, okay. Vx as some constant times e power minus half integral pt dt, because you see why I choose this one. X naught, in this example x naught should be a domain of the differential equation. Here you can see that such an equation, here in this my example I have the domain is x positive only, because x equal to 0 I have a trouble here. Higher coefficient of the highest derivative whose value coefficient is 0 at x equal to 0. So I have a trouble at x equal to 0. So that should not be, that point should not be x equal to 0, should not be a point of the domain. So I have x positive. So if I have to calculate in this way, I have to choose my x naught to be non-zero. So, that will give you unnecessary value, unnecessary calculations. So, instead I do the definite and indefinite integration when I solve this separable form. Okay. So, either this or this you will get. So, if I use that, what is my p? P is 4x by 4x square, that is 1 by t dt. So, 4x by 4x square, that is 1 by x, that is my p of x. P of x is 1 by x. So, p of t should be 1 by t dt. So, this will become e power minus half log t. So, this will become 1 by root t, right, t power minus half, sorry, this is again. So, that is pt px dx. This is indefinite integration. So, I have 1 by x dx. So, this is simply log x, that is going to be this. So, this implies transformation should be the dependent variable into x power minus half into, that is v into ux. This is what I use, this is the transformation. If I use this with this v, okay, v is this, with this what happens to this one? 1 by v v double dash plus px v dash plus qx. What happens to this value, this quantity, which is the coefficient of u? Okay. So, we will just see this 1 by v is root x, v double dash is minus half, v dash is minus half x power minus 3 by 2. So, this is going to be 3 by 4, sorry, this is this, and v double dash is minus plus 3 by 4 x power minus 5 by 2. So, I will write directly v double dash is 3 by 4 x power minus 5 by 2 plus p x is 1 by x times v dash is minus half x power minus 3 by 2. So, plus qx, what is qx? 16x square minus 1 by 4x square. So, that is going to be 1 by 4x 4, that is first is 4, 16x square minus 1 by 4x square is 4 minus 1 by 4x square into qx into v, right. So, qx into v. So, I have v here. So, if you have that v is x power minus half. So, this is equal to root x. So, you see that 3 by 4 x power minus 5 by 2 minus half x power minus 5 by 2 plus 4 x power minus half minus 1 by 4 x power minus 5 by 2. So, this will become root x power minus 5 by 2 coefficient is 3 by 4 minus half minus 1 by 4. So, minus 3 by 4, this gets cancelled. Okay. Half minus 1 by, so this is 3 by 4 minus 3 by 4, this one together cancel this. So, I do not have this term. So, what I have is 4 power x minus 1 by 2. So, this becomes simply constant. So, if this is constant, what happens to my equation? So, I have u double dash plus 4u equal to 0. So, this will give me what is the general solution of this equation. So, you will substitute ux as e power lambda x. So, that will give me, if you use this lambda square plus 4 equal to 0, that will give me lambda equal to, what is lambda? Plus or minus I 2y. Okay. So, this implies u1 of x, one linearly independent solution is e power I 2x. Okay. Other linearly independent solution is, these are complex roots, they are different. So, I will have e power minus I 2x. These are the two linearly independent solutions. So, that you have your ux c1 e power I 2x plus c2 e power minus I 2x, or in two different new arbitrary constants you can write d1 cos 2x plus d2 sin 2x. You can also write your general solution like this. This is your u. So what is your v? Y is actually, you want y is u into v. Okay. So this implies my yx, the general solution, is c1 cos 2x or d1, whatever, they are arbitrary constants, d1 cos 2x plus d2 sin 2x into, this is your ux into x power minus half, that is your v. Okay. That is all. So this is your general solution for x positive. Okay. So 1 by root x is not defined if it is x equal to 0. This is how you got the solution. So it has two arbitrary constants d1 and d2, so that this is the general solution. This is the general solution. Given equation. So this is how you can solve sometimes by reducing. So this is one example. You have many examples. So you can give as an exercise assignment. Okay, I'll give you problems, many problems. By transforming, putting into this normal form, you can solve certain equations. Okay, I'll give you problems as an assignment exercise later on. So this is one ad hoc method. Now let us see how this is. Otherwise you don't know how to find y1 and y2. If it's an equation with variable coefficients, some functions of x, either you should know one solution or then you can find the other, or if you can put it in this standard form you can find, or it should be Euler-Cauchy type equation where the y double dash coefficient should be x square, first derivative coefficient should be x, and so on. Okay, if you have in that form you can get your solutions. You can get your two linearly independent solutions, or with constant coefficients, or equations with constant coefficients you can get your two linearly independent solutions that will form general solution. Okay, so and you also have seen how to solve non-homogeneous second order linear ODE. So for that you need your y1 and y2. If you are given some equation, you first calculate its homogeneous solution. Homogeneous solution of the homogeneous equation as your yh. That will have two arbitrary constants and two linearly independent solutions of that linear homogeneous equation, that is your y1 and y2. Once you know this y1 and y2, you can find your particular solution by the general method called variation of parameters. Okay, we will see how it is solved. So variation of parameters. So let me solve how what we have is the equation. What we have is y double dash plus px y dash plus qx y equal to some fx. I have this full equation. Okay, x belongs to some domain I, can be full or any part of any interval in R. So what I do is I will consider the homogeneous equation. Okay, y dash plus qx y equal to 0. So this will have the solution yh of x as c1 y1x plus c2 y2 of x. Assume that I can find this y1 and y2 are two linearly independent solutions. You know for somehow. Okay, if I know one solution you can find the other like that, or you directly, if you are in specific form, you can find your own y1 and y2, so that you have a general solution for this homogeneous equation. Now how do I find a particular solution yp of x that satisfying y double dash plus px y dash plus qx y equal to fx, the given equation? How do I get this yp? So this is called method of variation of parameters. So you know that, already know that this is the form that satisfying the homogeneous equation with constants as c1 and c2. If I can vary this c1 and c2 as functions of x, I can hope my yp in this form c1x y1x plus c2x y2x. You look for in this form as non-constant functions c1 and c2. If I look for my solution y in this form, then I can hope to find my particular solution. I find what is my C1 and C2 as functions of x, so that I know my, if I can find my C1 and C2 as functions of x, if I by imposing certain conditions and then finding this C1 and C2, I can calculate my yp. Once I know my yp, sum of yh and yp will be a general solution. Okay. So how do I get, so if I look for in this form, so it has to satisfy this equation. So calculate yp dash. What is this one? C1 dash y1 plus C2 dash y2 plus C1 y1 dash plus C2 y2 dash. From this I can calculate. Then what is my yp double dash? C1 double dash y1 plus C2 double dash y2 plus C1 dash y1 dash plus C2 dash y2 dash. I have to integrate this also, that will give me C1 y1 double dash plus C2 y2 double dash plus I have to differentiate C1 and C2 also. So C1 dash y1 dash plus C2 dash y2 dash. Okay. So these are common, this one and this one you can combine, so you can make it 2. So I remove this. Same way this also I can remove and put it here as 2. So this is what is your yp double dash. This now you substitute into the equation, non-homogeneous equation, to look for some C. Okay. See, I want some particular form of C1 and C2. Okay. It is not that I want a general C1 and C2 that satisfies that. See, I am not looking for some all C1 and C2 such a way that this yp is the solution. I want some C1 and C2. So I can always impose conditions on C1 and C2 such a way that I can find C1 and C2. Okay. So when I choose my yp as this, I choose my yp dash is this. So here itself I impose my condition. I choose this as 0. If I impose not this, I impose this is my condition. So if I impose like this, this is equal to 0. Okay. If I impose this as 0, then what is my yp double dash? So I have one equation, C1 dash y1 equal to plus C2 dash y2 equal to 0. So this is my equation 1. I imposed, I choose so C1 and C2 in such a way that this quantity is 0. You know already y1 and y2. Okay. You know y1 and y2. So I am looking for C1 and C2. So if I know my C1, y1 and y2, I choose my C1 and C2 in such a way that this quantity is 0. This is equation number 1. So that this quantity will be there for yp dash. Then what is my yp double dash? I have to differentiate this part alone. So this will give me C1 y1 double dash plus C2 y2 double dash plus C1 dash y1 dash plus C2 dash y2 dash. Okay. Now you substitute yp double dash, yp dash and yp into the equation. If I do this now, you get C1 y1 double dash plus C2 y2 double dash plus C1 dash y1 dash plus C2 dash y2 dash plus Px times C1 y1 dash plus Px C2 y2 dash plus Qx C1 y1 plus Qx C2 y2 equal to Fx. So what is this? This is equal to, what is the coefficient of C1? C1 is y1 double dash plus Px y1 dash plus Qx y1. So you see this one, and this one. This is the, I collected these terms. Similarly, you can collect the coefficient of C2 as this one and this one. So you have y2 double dash plus Px y2 dash plus Qx y2 plus whatever the remaining is what? C1 dash y1 dash plus C2 dash y2 dash equal to Fx. And I already know what is my y1 and y2. y1 and y2 are satisfying homogeneous equations. y1 and y2 are what? They are the satisfying homogeneous equation, this one. So, these are 0, that means these are 0, okay. These are 0. So, you can remove this. So, what I am left with after substitution, I will have C1 dash y1 dash plus C2 dash y2 dash equal to fx. So, this is your equation number 2. So, if you solve 1 and 2, I can find my C1 C2 satisfying these two, okay. If I can find C1 C2, then you go and substitute those C1 and C2 here, that will be the particular solution, okay, as simple as that. So, 1 and 2 you can put it in this form, implies what is this one? This is actually equal to y1 y2x, y1 dash y2 dash, unknown C1 dash C2 dash, these are your functions, unknowns, equal to 0 and fx. You know how to solve this second order system. What is the matrix? It is the determinant of the matrix, C1 dash C2 dash equal to, what is the determinant? 1 divided by determinant of this. What is the determinant? W of y1 y2 of x. This is simply Wronskian. Determinant of y1 y2, y1 dash y2 dash is already you know, y1 y2 dash minus y2 y1 dash. This is exactly your Wronskian of y1 y2 of x, because these are functions of x, okay. So, this is your Wronskian times what happens to A inverse? What is A inverse? What is your A inverse? What is, if it is A, B, C, D, what is its inverse? 1 by AD minus BC, AD minus BC minus DA, right, DB minus BD 0. Yeah, this is what it is. So, you have to interchange this and this. So, y2 dash, y1 here, and then minus y2 as it is minus y1 dash. This is the inverse I wrote. Now, I write the right hand side is this. So, what is this one? This is equal to 1 by Wronskian W of x I write. This is exactly minus y2 of x into fx as one element, okay. So, let me write this as, so this is now matrix, okay. So, first element is 1 by wx into minus y2 of x into fx by this, that is your first element. Second element is y1x fx by wx. These are the two elements, okay. This is my C1 dash C2 dash. Now, having known this vector C1 dash is this, C2 dash is this, what is C1 dash? dc by dx equal to minus y2x fx right hand side divided by wx. You can directly integrate from, so this will give me C1 of x as, simply integrate minus integral y2 of x fx by Wronskian of y1 and y2 dx plus some constant. So, I take it as 0, okay. So, because I only need some non-constant C1. So, similarly C2 dash if you choose dc2 by dx is y1x fx by wx. So, this will give my C2 of x as with y1x fx by wx dx. So, you can see C1 will be minus with y2, C2 will be plus with y1. So, you can remember this. So, this will give me finally what is my yp of x. So, you have to replace this with C1 into y1. So, C1 y1 minus y1x into this integral y2 of x. Now, I change the x as a dummy variable y2 of t f of t dt by w of t plus C2 into y2. So, y2 of x, C2 is y1 of t f of t divided by w of t dt. So, you can actually have the form of your particular solution as integral y1 of t y2 of x minus y1 of x y2 of t, because this I can take it inside, this is only function of t, this integral is with respect to t. So, I can take it inside because it is a function of x, this divided by Wronskian of t. So, which is y1 y2 y1 of t, or you can write, you know what is the Wronskian of y1 comma y2 of t, this with dt. So, into f of t, f of t is I missed, so both sides. So, this is what is your particular solution. If you can calculate this, if you know y1 and y2, I can calculate this one, and once I know given non-homogeneous term f, I can calculate this integral to find the particular solution yp. Okay. So, I give you some example, how do we calculate this. So, let me choose some simple example. So, example how do you solve this non-homogeneous equation. So, y double dash plus y equal to cosecant of x. Okay, let us do this cosecant of x. So, what is the homogeneous solution? Solution of homogeneous y double dash plus y equal to 0. By early method, sin x plus cos x will satisfy. So, I write directly y h of x is c1 cos x plus c2 sin x. So, this is my y1 x, this is my y2 x, and what is my yp then? Once I know my two linearly independent solutions cos x sin x, this is the general solution of the homogeneous equation. Okay. So, yp of x will be equal to y1 y2. So, the integral y1 of t y2 of x. So, cos t sin x minus cos x sin t, because other one is y1 x into y2 of t, all divided by what is the Wronskian of y1 and y2, cos x sin x, derivative of this minus sin x cos x, this determinant is 1. Okay. So, you have simply 1, f of t is cosecant of x dx. So, this is what is the from this formula. From this formula we have written my particular solution directly. So, this is equal to, so this means sin x cosecant x, this goes. So, you have cos t dt minus integral cot x into sin t, this is f of t. So, it should be cosecant t dt, cosecant t dt. So, what you have is, so this integral value equal to cos t sin x into sin x, you can take it out. So, integral cot t dt minus cos x comes out integral dt. Okay. So, this will be equal to, what is your particular solution, minus sin x into log modulus of sin x. Okay. Here minus, so this is going to be x. So, I want finally function of x. Okay. And definite integration means I should have, okay. So, another thing is, only if you do the definite integration you can write like this, otherwise you just use this form. Okay. So, we just use do not use this form. If you are doing this, you can use some definite integration x naught to x, okay. X naught to x you can use, otherwise you can use this directly form. So, if you are using this form x naught to x, x naught to x, if you are taking this inside, you can use that way, okay. So, C2 in this C1 you can calculate also from x naught to x. So, C1 at x naught is an arbitrary constant that I can take it as 0. So, you can take it from x naught to x, no, it is not an problem, okay. So, if you do like that, so you have x naught to x. So, if you do that way, so x naught to x, x naught to x dt. So, this will be log sin x and log sin x naught. So, that I can choose it as some x naught which is in the domain, okay. So, what is the domain? So, once I choose what is x naught should be in my domain. So, this x naught should not be such a way that sin x is 0. So, should not be equal to n pi, n is from the natural numbers. So, you can choose anything anyway that is not contributing, because that constant I do not want to take in this integration. Constant you will get log sin x naught, okay. Log sin x naught into this is some constant, okay, that some constant times sin x, that also that is I already know from the whose solution I already know from the homogeneous equation. Ignore the contribution from the lower limit, because that only gives you some constant times solution of the homogeneous. Having known two linearly independent solutions of homogeneous equation, we can find a particular solution as a combination of these two by varying the constant as functions. It is called the method of variation of parameters. That is what we have seen with an example. So, in the next video we will have this is not the only way, this is the most general way to find the particular solution from the method of variation of parameters. In the next video, when the non-homogeneous term is a combination of 3 elementary functions such as polynomials, sine or cosine function or exponential function. These 3 elementary functions and its combinations if you have as a right hand side to your second order linear differential equation, you can find you do not need to use method of variation of parameters always to find a particular solution. So, when you have these simple elementary functions, combinations of these elementary functions, and in your right hand side you can apply a method of undetermined coefficients, in which the principle of this method is you annihilate the right hand side, because you know these simple functions satisfy some simple differential equations. So, that particular differential equation operator, if you apply both sides of the equation, given equation, so you right hand side you make it 0. So, we annihilation process, we annihilate the right hand side. So, with this annihilation process we try to get the form of a particular solution that you substitute into the given equation and find those constants. So, this is the method of undetermined coefficients that we will see in the next video. Thank you very much.